Alright, hello everybody. Welcome to lecture 14, translation 2. Funny enough, I took a look at this lecture and I realized that it's actually really short because I already went over the majority of it. So this should be like probably one of the shortest videos I've ever done. So yeah, I've already done videos on all of this stuff for lecture 13. I covered all this translation stuff. I explained all of this and how this works, what you should be looking at. So I'm not gonna even bother explaining this. If you have questions, I also went over this in my workshop. So there's 2 videos up about all of that content. There's one video up for the lecture, and the second one is just people asking me questions about translation in the workshop. So I'm not gonna go over that. But this is a new slide that wasn't in the previous video. We ended on this slide when we left off. So for this slide, I want to get across the idea that you use different forms of energy in translation. And in this case, what we've got is both ATP and GTP. So every tRNA that you use requires a single ATP. And you know that's to make the amino acyl tRNA. Basically what you're doing is you're activating this amino acid by attaching it to an ATP to make an adenylated amino acid, this thing right here, and then you use your tRNA and then you attack this carbon right here, and then you kick off this bond and then you release AMP. And this reaction is favorable because we release pyrophosphate, which you can cleave for 2 phosphates to get like 30 kilojoules of energy. So that's ATP. So every amino acyl tRNA that you make is 1 ATP to produce that. And then you get to the actual ribosome portion of it, and during the translation, specifically this is the elongation phase, right? This is not accounting for the initiation or the termination phase. This is specifically talking about elongation. So if a question is asking you to talk about elongation, termination, and initiation, you're gonna have to look at all 3 of these. I just realized my mic is like cutting out a bit, isn't it? That's a bit weird, but I'm gonna try and that's a bit too quiet. Okay. Yeah, okay, but basically what we're doing is we're gonna take a look at this and say, okay, EFTU, for every amino acid it brings, it's gonna use 1 GTP. And then for every translocation that occurs, that's for every amino acid brought, there's another GTP used by EFG. So there's 2 GTPs used per amino acid brought in, and 1 ATP used for every amino acid brought in, because there's 1 ATP required to make that amino acyl tRNA. So 3 pieces of energy are required, essentially. And this is a a slide talking about like why a lot of these things are multi-subunit and like what's the beneficial function. And the beneficial function, from what I understand, for why you would use multiple subunits in this case, is because when you use multiple subunits, it allows for tighter regulation and it's better regulation. It allows for the environment to control more of what's happening. So like if you only had 1 subunit, then it would maybe take 1 check to actually begin the process. But in this case, you're not going to start translation or transcription or splicing, so any of these, unless like everything is perfect. And that's kind of exactly what you want. You want to make sure that these processes are very specific to specific points in time, because you don't need them to happen when, like, I don't need the translation to happen, for example, when maybe I'm already like super high on proteins. I don't know. Maybe I've already got a bunch of proteins. So maybe there's like a system in place for the body where it's like, oh wait, I've already got enough proteins, I don't need to make any more. And maybe it tells the ribosomes to shut off, and it shuts off certain subunits of the ribosome, and so that stops it from working. So that's kind of like the idea that I want to get across with these multi-subunit complexes. They're much more complex with regulation, and that allows them to be a lot more dynamic and reactive and adjustable to the environment that they're in. This slide is really confusing when you first look at it, All it's trying to show you is like these like dotted circles, like these dotted circles. All they're trying to say is that like most of the conformational states that we have are actually not. They're actually not visible. You can't actually see them, and the reason is because we just don't have the scientific techniques to look at them. So we've captured, you know, imaging of the sections that are circled in solid lines, but like all these like dotted circles, those just show you know, cases where we haven't been able to actually see what the conformation exactly looks like for the ribosome. Because remember, the ribosome is going through these conformational changes so quickly. I can't remember the exact, it's like 10 to the 7th like amino acids per second or something. It's really fast for the catalytic activity of this thing. So we don't have the technology to actually see all of the states of the ribosome at every given time point. This idea here about tRNAs undergoing conformational dynamics, all it's talking about is the tRNA also changes shape a little bit and, you know, is kind of conforms to the ribosome structure to allow itself to actually help with the docking of the tRNA itself, and then also the release of the amino acid on it. So there's a bunch of different tRNA structures, and you know it suggests, you know, like a large degree of flexibility. So tRNAs are pretty flexible as well, and like they can fit into the active site in many different ways. So, and then this whole like mutually induced fit is something you guys have seen in 440, where it's like the tRNA binding actually causes the ribosome to bind stronger to the tRNA. So it's like the tRNA binds, right, to the binding site, and then because it binds, it causes even stronger binding because now the ribosome basically hugs that tRNA. So the tRNA binds, causes a conformational change in the ribosome, and now that ribosome binds even tighter. So, and like this kind of thing is only possible in complex protein assemblies. So like when you have multiple subunits, by the way, a single subunit is not going to move in this way, but multiple subunits together connected through different interactions, that will do it. So we've got R proteins here. So R proteins serve as like flexible glue to help with the dynamics. So dynamic, when it talks about high dynamics, it just means that it's very like liquidy and movable, right? It's not very static. So basically the ribosome is very fluid, if you will. So it says that many R proteins have long tails anchored into the rRNAs. So the rRNAs kind of serve as the anchor for the ribosome, and then the R proteins kind of act as like little swings and stuff like that. And those are a little bit different from the rRNAs because, like, you know, the rRNAs, while those are there to make sure that the ribosome is stable, the R proteins are there to actually kind of you know, swing around and serve as like the reactive sites so that, you know, we can actually do translation, if you want to think of it like that. And also, I just want to make this clear as well. I want to make sure this is very clear. For when we're talking about these long tails anchored, it's like those are amino acid tails, basically. So we have these R proteins. They have these long tails, like the histones did. The histones, remember, had like very long tails that were coming out of them. So these R proteins also have long tails, and they basically tie themselves to the rRNAs, which is how they kind of anchor themselves. Otherwise, they would just like float around. So that's what I mean by that. And because they have these long tails, they're able to move very easily. They're very mobile. And this is just a slide showing you the things that you need to know. I think this is a helpful slide. It shows you where you need to know. Like you can see here, you need a GTP at the start. You need, for elongation, you need a GTP. You need another GTP. You also need an ATP. Remember, for the formation of the actual amino acyl tRNA. That's not shown here, but you do. And so every amino acid added requires 2 GTPs and 1 ATP. And then the termination and recycling requires 2 GTPs. And that's all listed for you in this table as well and all that jazz. But, yeah. And also, yeah, there's early termination and kinetic proofreading and stuff like that. But yeah, that's actually all I have for this video. That I realized, like when I was, like I said before, I realized that when I was looking through this lecture, that's literally just taking the stuff from last lecture and elaborating a little bit on it. So I just took the slides that I hadn't gone over and was like, okay, these are pretty simple. Let's just talk about them real quick. Because I know your guys' exam, I believe, is next Wednesday, I believe. So, yeah. Hope this stuff makes sense. And I hope to see you guys next week for the workshop. I plan on having an exam review. So, yeah, hope to see you guys there. Have a good one. Happy studying.